Okay, so first I want to make a few remarks about the relationship between relations, and got to get the pen going. Oops. Relations, functions, and nondeterminism and determinism. So these are some fundamental things. So recall that I think this idea makes the notion of non-determinism and determinism much simpler in terms of mathematical definition. So recall that given sets A and B, if R is a subset of A cross B, then R is a relation. So that's what it means to be a relation. And recall that also, remember that, this is Cartesian product. And it's defined as the set of pairs x, y such that x is in A and y is in B. So, for example, this Cartesian product of 1, 2 cross AB is equal to the set of all pairs. So, where the first element comes from, this is my A, this is my B, and so we've got 1A, 1B, 2A, and 2B. Okay, so that's the Cartesian product. So that's what a relation is. Now, oftentimes we draw pictures of relations that look something like this. We might have like, A, and we've got 1 and 2. We've got B, which has A and B. And now, one of the relations that is in here, which is a subset of the Cartesian product, is, for example, that 1 is related to A and 1 is related to B and 2 is related to nothing. So if I call this like, R, let's say R1, then R1 is the set of pairs 1A, 1B. Okay, so now that's Cartesian product. What we don't, in a function, I don't know what it's doing. Okay. Shapes. So anyway, in a function, f, say f, call it f is a subset of A cross B with the additional constraint that This example up here does not happen, where you don't have one going to A and one going to B. That can't happen. 1 point over from A cannot get mapped to 2 different points in B. So what we want to say is, how we say that in mathematics is we say for every x in A and for every y and z in B, if the pair xy is in F and the pair xz is in F, then that implies that z or y, let's say, is equal to z. So this property here is called functionality. What is wrong here? I want to just be in a so that's functionality. That's what that property is called. So functionality means nobody can go, no point in A can get mapped to more than 1 point. So it can have this, that would be a function. If this is 1 and this is 2 and this is A and this is B, I can't add in the I can't add in this one. That's got to go away. Now I can put in, for 2, I could make 2 go somewhere. I could make 2 go to A. So then both 1 and 2 map to A. This doesn't violate functionality, because functionality just says no point here can get mapped to 2 points over here. All right, so this is pretty straightforward. But when we are, when we're, okay, I lost my edge there. I'm having a little trouble. I'm just learning this thing. Okay, so when we have a relation that is not functional, so is non-deterministic. In other words, it can have from A to B. I could have one related to A and one related to B. Very interesting. How do I get this to stop doing this? Anyway, okay, so I got one related to A, one related to B. And, we could also have 2 related to B. So this is a perfectly sensible relation, well, as this one was up here. And the non-determinism is that if you think of this as a state, it means that you can go to the state over here, which is A, or the state over here, which is B. So you can transfer to different states. Now, if you have a function, then it's deterministic. So you might recall that the definition in the book for the definition for determinism for example, the big step semantics on arithmetic relations says that the property of determinism is formalized that for every state S and configuration, let's say E, which is an expression. I should call it A1. And let's say so I apologize. Let me back up just a little bit. Let me say that this is something in states. And then for every A expression, and for every V, which is an int, and we'll actually need V1 and V2. We have the property that if S says under S, A evaluates to V1, and also under S, A evaluates to V2, those two things together imply that V1 equals V2. And so this was the definition of what it meant for the big step semantics over arithmetic expressions to be deterministic. So if you go back up and look, you're basically saying, look, from A, you're mapping to V1, and from A, you're mapping to V2, so that must be that V1 equals V2. And we saw that up here in the definition of functionality. We saw that X goes to Y, X goes to Z, that means Y is equal to Z. So determinism looks the same as functionality for a relation. So I hope that makes that concept a little bit simpler. It seems very, there's a lot of philosophy. Philosophers will talk about, is the universe deterministic or is the universe non-deterministic? In this case, we're talking about a very precise mathematical definition. Although this is essentially what they mean there. You can't have some non-deterministic behavior if you're deterministic. Okay, bye.